We have with us Professor Sudip Misra, who is the professor and Abdul Kalam Technology Innovation National Fellow in the Department of Computer Science and Engineering at the Indian Institute of Technology, Kharagpur. He received his PhD degree in computer science from Carleton University in Ottawa, Canada. His current research interests include wireless sensor networks and Internet of Things. Professor Misra has published over 350 scholar research papers and 12 books. He has won 9 research paper awards in different conferences. He was awarded the IEEE ComSoc Asia Pacific Outstanding Young Researcher Award at IEEE GlobeCom 2012 California in USA. He was also the recipient of several academic awards and fellowships, such as the Faculty Excellence Award at IIT Kharagpur, Young Scientist Award at the National Academy of Sciences, India, Young System Scientist Award, Young Engineers Award, Governor General's Academic Gold Medal at Carleton University, the University Outstanding Graduate Student Award in a doctoral level at Carleton University, and the National Academy of Sciences India Swarna Jayanti Puraskar. Samsung Innovation Awards 2014 at IIT Kharagpur, IETE Biman Sehri Sen Memorial Award 2014, and the Careers 360 Outstanding Faculty Award in Computer Science for the year 2018 from the Honorable Minister for Human Resource Development of India. Ladies, gentlemen, and others, with a loud applause, for our next session, Data in the Context of IoT, I bring to you Professor Sudip Misra. Over to you, sir.
Okay, so thank you. I'll just take a moment to share my slide. I hope that I am audible enough.
Yes, sir, you're audible and you're visible as well.
Okay, thank you.
We can see your slides as well, but yes, it's presenting.
Yeah, thanks for the confirmation. Okay, so first of all, thank you, PLD conference, for inviting me to share some of the knowledge and experience that I have got while working on IoT for the last decade and a half or so. What I'm going to do now is to share with you some of the concepts that are important in the context of data handling for IoT. And so first, this is the way I have segmented the session today. First, I'm going to present some of the basic knowledge that is required in the context of data handling for IoT. And thereafter, I'm going to talk on some of the research works that we have done in the Smart Wireless Applications and Networking Lab, the SWAN lab at IIT Kharagpur. So I think many of you who are into the IoT space, you already are aware of the research works that we do in the SWAN lab. I'm going to share with you some of them. So what I'm going to do is, because the time is very short and limited, I am going to give you only a glimpse of some of the different works, and I will leave you with the full reference of the research works that have been published in the public domain, so that if you are interested and are keen to know more about the work, you can visit the corresponding website and get a look at the work that has been reported in that particular paper. So this is what I have planned for today. So first of all, let us try to take a peep into some of the basic stuff. So I think most of the audience over here, all of you are familiar with the term IoT. However, for the sake of completeness, let me just give you a high-level view of what IoT is all about. So as most of you know, and those of you who do not know, IoT is about Internet of Things, so which means that the physical objects that we all use, that we see around us, like the chair on which we are sitting at present, the projection system of a conference room, the air conditioning system of the room, and basically any physical object that you can think of, including the air conditioner, the washing machine. So any physical object, right, including the toothbrush that you have used in the morning and the rice cooker that you are going to use to cook your lunch. So these are all like candidate objects which can be interconnected, internetwork to form the Internet of Things. So I think this is something that most of you are familiar with. So without spending too much of time on it, let me just tell you that IoT has become very popular due to the large number of different types of use cases that IoT basically helps in rendering, right? So different types of use cases. So use cases in the space of smart homes, in smart cities. So in India and throughout the world, there has been since the last 5-6 years or even more, there have been a lot of thrust on developing smart cities or transforming existing cities to make them smarter, right? So whenever we are talking about smartness of any kind, naturally sensing, then automated processing of data, and doing stuff without any human intervention. So these are some of these different things that come to our mind, so that so we can enjoy some intelligent services at our at our homes, wherever we are, we can enjoy these different services. So not only homes, actually, I mean, it can be anywhere, right? So on the road, in our offices, or anywhere, so depending on the use case that the IoT particular IoT implementation basically tries to achieve, right? So so as you can see in this particular picture in this slide, so what we have is kind of a neighborhood where there are different types of typical civic amenities, etc., and these are IoTized, right? So in the sense that they have different IoT devices which can not only sense but also communicate. The data can be processed, so on and so forth. So you have such kind of data, such kind of implementation. So these data, basically from these different sensor-enabled devices, they can, I mean, so these devices basically, so they send a lot of data, right? So this data will have to be handled. So the data has to be ingested, it has to be transformed, it has to be sent to the sink, and thereafter, so the data will have to be analyzed, right? So you store the data, you analyze the data, so the analysis comes in the form of, like, starting from basic statistical analysis to many advanced machine learning, deep learning kind of analysis that can be undertaken, right? And for storage, basically, typically, so previously it used to be like server, and then it it used to be like server farms, etc. But this concept has transformed, and nowadays almost like any kind of IoT implementation talks about storing the data and analyzing the data at the cloud, right? So even so when it comes to analysis, basically I will talk about it later. Not only at the cloud, but also there is something called edge computing, fog computing, and so on and so forth. I mean, these are certain terms. In case you are not familiar with, do not worry. I have tried to make the slides as much inclusive as possible, so that so those of you who do not have the requisite background, you can also follow whatever I'm saying. So this data will have to be handled, right? So whenever you are talking about this kind of how do you handle the data, so many different issues come into picture. It's not about running some machine learning algorithm or some statistical analysis and you get the results. It's not about that. I mean, of course, I mean, that also has a lot of challenge, and that is where a lot of machine learning experts put their time to understand what is in the data. However, so there are a lot more things into it, like how do you secure the data, right? How do you secure the data? Not only the data, actually, the actual devices. How do you secure the devices, the data that come out of it? Where do you store the data? Centrally distributed, or I mean, do you have something else, like so some kind of a mixed or a hybrid kind of model, right? So many different factors that come into picture depending on the specific application requirements. So I'm going to touch upon some of these in the next while. And then, as I said before, I'm going to switch my gear and I'm going to talk about some of the research works that we have done, and keeping in mind once again that, so I'm not going to go through these research works in detail because, I'm going to just give a glimpse of these. The purpose is not to talk about a particular research paper in too much of detail, but if you are interested, we can take it offline. So when we talk about data, right? So whenever we talk about data, data has certain characteristics, and these characteristics of this data, these also vary from the particular application domain or particular deployment, so according to the particular deployment or the application or the use case, so the nature of the data also varies. However, broadly, we can classify the data in the context of IoT to be of three different types, right? One is the scalar data, the other one is the vector data, and the other one we can talk about is the multimedia data. Although there is an overlap between multimedia data and vector data, right? So you can think of multimedia data to be vector data. So the scalar data and the vector data, I'm not going to go through into much of detail, but those of you who understand the difference between scalar quantity and vector quantity, the same concept basically applies in the context of data as well. So scalar data and the vector data, basically, in scalar, you are talking about only the magnitude of the data, right? So in the context of vector, basically, we are not only talking about magnitude, right? So, but also the direction, right? Both are important. So for example, like temperature, right? So temperature is scalar quantity. So the temperature data is a scalar data. However, if you are talking about accelerometer gives you acceleration, right? So acceleration of a particular body on which that particular accelerometer sensor is deployed. So accelerometer data is basically a vector data, right? And the third one is the multimedia data. So in multimedia data, we are talking about, so some cameras or, which can be video cameras or which can be still cameras, etc., which capture multimedia, for example, image, video, audio, and so on and so forth, right? So these basically are part of multimedia data. Now, the complexity, level of complexity also varies across these different classifications of data, which I'm not going to talk about too much. So how do you handle the data? That's the whole, ball game. So how do you handle the data, right? So, so this data, first of all, the data that comes in will have to be stored somewhere, right? So the data will have to be stored somewhere, and then you execute different, algorithms, some computational intelligence you execute on this data, which are stored somewhere. So like a server farm or the cloud, and then you can get a lot of insights about this is the beauty of the data, right? So now in the context of IoT, what has to be kept in mind is that so the data, typically for most of the IoT applications, the data will have to be handled in real time. So it has to be detected. The data will have to be detected and handled in real time. So as you can understand that anything that we talk about in real time, there are a lot more challenges than doing it offline, right? So so here also the same thing, like, so just take an example. For example, if you are talking about an IoT deployment where you have camera feeds that are coming, and you need to basically ensure surveillance of a particular terrain, right, or a particular building or infrastructure, right? So even like a couple of seconds of delay in analysis of the data, that makes a lot of difference, right? So that's not going to be useful. So it is very important to analyze also in real time, right? So you have to detect, you have to collect, you have to store, and you have to analyze the data in real time and present the data in an appropriate format to make it much more usable and user friendly for the users to make sense out of it. So, so there are different, so there are different advantages of, handling the data. Not only, examining the data, revealing trends, but also there are so many different things, like, you can get a lot of insights. You can mine the you can, using intelligence, you can mine the data, right, to get something. You can get some hidden correlations you might be able to uncover, right? Or you might be able to see certain patterns which may not be as such visually visible if you simply visualize the data using certain visualization tool, right? So you need to get little insight and mine the data in order to get a lot of insight into the data. So how do you handle the data, right? So as I told you, like so previously it used to be like data centers, and nowadays cloud computing. Although so there is a lot of overlap between data center and cloud, because ultimately whenever you are talking about cloud, it's kind of an overlay over the data centers, the traditional data centers. So in a sense, actually these are more or less the same. But ultimately, what we are talking about is to store the data. And this data nowadays, we are talking about storing this data in the form of reservoirs, which are called data lakes, right? So these are like giant data reservoirs, right? So for this, basically for the storage, you have the cloud computing. For the analysis, you have different machine learning, deep learning, as a whole, artificial intelligence techniques, etc., which will have to be kind of percolated into these data lakes in order to get a lot of insight into the data. And that is where the beauty of IoT and the so the implementation of IoT basically will become much more meaningful. So one thing that I was telling you is to do the things real time, right? So if you are sending all the data to the remote cloud or the remote data center, etc., that basically is useful, but at the same time, it's going to be a little bit delayed because the signals will have to propagate through all the way up to like the remote data center or the cloud, etc., and that's going to cost some time, right? So what we can do is that instead we can execute certain lightweight machine learning algorithms or certain statistical analysis we can do at the edge, right? At the edge means like close to the source, as much close to the source of the data, the origin of the data, as much close as possible. So that's basically all about edge computing. Then so between edge computing and between edge computing and cloud computing, there is another concept which is called the fog computing, basically. There is a fog layer, etc., etc. But the main thing is that you have edge computing, fog computing, cloud computing, etc., which can help you nowadays to store the data, to analyze the data, and depending on the application requirements, where you are going to do the processing, whether at the edge or the fog or the cloud. So these are all dependent on that. So there are certain characteristics of cloud computing, so which I'm not going to talk about in detail, just to save some time for talking about the research works that we do in our lab, which I've saved towards the end of this particular talk. So cloud computing, so basically, these, in the form of like, offering computing infrastructure, or offering computing platform or software, as services. Cloud computing service models have been proposed traditionally with these three different service models, but there are so many different other service models also which have come into picture over the last couple of years. So I myself, in our lab, we came up with few other service models for use of cloud computing in the context of IoT, right? So not only these three are definitely important and core to cloud computing, but there are different other service models which are important. So one of these actually I will talk about later. So in the context of safety, because whenever you are talking about industrial deployments of IoT, which in short is called industrial IoT. So in industrial scenarios, basically you have certain requirements with respect to safety. So how do you handle safety? So I'm going to talk about that also. And for that, whether you can have certain cloud computing model which can cater to these kind of requirements. So cloud, data center, all of these play a huge role in terms of storing the data, managing the data, organizing the data, getting insight into the data. So these are very important. So here, actually, what you see in the picture in front of you is kind of a modern city kind of scenario where you have a lot of sensors that are deployed, sensor nodes, the IoT nodes that are deployed, and you can also have some UAVs which are sensor equipped. So all of these throw a lot of data which will have to be stored in private cloud, public cloud, etc., etc. So another thing that is very important is that in the context of cloud also, so there are so many different ways in which you can save the data, you can store the data, you can handle the data, right? So private cloud is basically restricted to certain organizations and so on, and public cloud is made public, like the public cloud services that are available for payment, etc., right? But the thing is that sometimes, for certain requirements, certain deployments, basically you need to synchronize this public cloud and the private cloud, right? So if you synchronize, then how do you handle the analysis of the data that are stored in each of them? So for that, actually, there are concepts called federated learning, which help in handling this kind of distributed storage of the data. So data lakes are there where you have repositories, giant repositories, where data are collected from different sources, stored in their original state, etc. So if you recall, so I told you about the different types of data, right? So for so whenever you are talking about data, you are talking about scalar or vector or multimedia and so on. So depending on the type of data, right? So if you are talking about some kind of a structured data, then you can use your SQL-based query mechanisms, right? That we know conventionally for databases to, to run queries and get results of the queries and so on. However, there is something called the NoSQL. These are not new terms, right? These have been there since, big data, etc., became popular in the last decade or so. So NoSQL database basically, so they help in handling the data which is stored in the unstructured form, right? So for example, newspaper feeds, for example, YouTube videos, for example, camera feeds, right? So these are unstructured data, right? So how do you run queries, or how do you analyze the data on unstructured? So for this, actually, you need something called NoSQL. So fog computing, cloud computing, etc. I already told you, AI can help you to get insight into the data, to recognize certain patterns, to see, to analyze any kind of abnormality or aberration or anything like that. Or it can be also used to predict what is going to happen in future. So predictions, actually, we do a lot of predictions in our lab on a lot of IoT projects where we use a lot of these machine learning, deep learning based techniques for these predictions, right? Because so for example, I'll just give you an insight. We have the AmbuSense project, right? So which has become quite popular in the country, and where we are doing what we are doing is we are doing ambulatory monitoring of the patients, right? So it is very important, like when a patient travels in an ambulance for a long stretch of road, it is very important to predict what will be the health condition of the patient, maybe after half an hour or after 1 hour, right? So accordingly, you can take certain decisions about how to handle the patient. So whether you want to continue the journey, or whether you want to take to a local hospital, or so that kind of prediction so are very important. So I just give you a simple use case where predictions are important in the context of IoT deployments. However, there are so many different other use cases that are there, and you can conceive of where predictions can become very, very useful. So big data, right? So I was talking about big data because the data basically that comes from these IoT deployments, these typically have the characteristics of a big data. So you will have to analyze this big data typically in real time, but not necessarily, because if you are talking about, let us say, agricultural deployments, right? So we have agricultural farms at IIT Kharagpur and neighborhood where we have IoT installations in place, right? So the nature of the data over there, so we are talking about soil moisture, we are talking about soil temperature, etc., which do not change too fast, right? So you do not need to execute real-time analytics in such kind of data. However, if you are talking about surveillance, right, you need to definitely run real-time analytics on this kind of big data, right? Because these are big because there are so many different characteristics like volume, veracity, then so many. I'll talk about that shortly. There are different V's which characterize the big data, which are very important. So variety, volume, velocity, right? These are the three V's traditionally which characterize big data. So the complexity that is in place in terms of this volume, velocity, variety, etc., and the complexity of the data, inherent complexity of the data, that will have to be utilized in order to analyze the data and to get insights or predict or classify the data, right? So big data has been there. Nothing different. We are not talking about anything new. However, in the context of IoT, there are certain characteristics of these kind of big data. And these are distinct from the conventional big data that we used to talk about, right? So these are some of the different characteristics that I have, noted for you. So the first one is basically IoT big data requires more robust, agile, and scalable platforms. So let us try to understand. Agility is very important in the context of IoT. And if you are talking about a highly dynamic kind of IoT deployment, agility is paramount. So how do you cater to the requirements of IoT? So first of all, you are getting big data for sure, but it's agile big data. High velocity is extremely high, right, of the data, right? So how do you handle that? So scalability is also very important because so we are talking about like large, massive IoT deployments typically, right? So where there are thousands and thousands of nodes which are deployed in a particular facility or a particular terrain. So this is this is very characteristic of IoT, right? So faster data generation, data coming through a single pipe. You can think of a single pipe through which data of different formats come through, right? And what happens is these are not unified in any way because these data, they come in different formats because the devices themselves have come from different vendors, and there is no uniform standard for these different types of data, right? So so there are different formats of data produced by different IoT devices developed by different vendors who do not follow any particular standard for this data. So these are all coming through a single pipe conceptually. And how do you handle this kind of data? This is a characteristic which is typical of IoT and which is typically not observed in any other conventional type of big data, right? So faster generation, handling data of different formats coming at the same time. Volume has been there, but here actually in the context of IoT, we are talking about high volume of this kind of different formats of data, right? And you need to do real-time processing of this kind of data. Real-time processing is important. You cannot afford to store it in a in a database or somewhere and then take it offline and do some analytics, etc., etc. And by the time you analyze, if you are talking about surveillance application, basically, the thief has already stolen the stuff and has left the building, right? So you cannot afford to do that. You need to do everything online, right? So you have to do it in real time. So this is what I was talking about. So when big data basically this technology was popping up, those days basically so people talked about 3 V's, then it extended to 5 V's, 7 V's, and now 8 V's, right? So these are all these 8 V's like velocity, volume, viscosity, etc. So these are like the different types of characteristics of the big data that are observed in the context of IoT, right? All the 8 V's are important in the context of data from IoT. So how do you handle this kind of data? So you need to use different tools for analytics, right? So these tools, some of these tools are already there, off the shelf tools you can use, or some of these tools will have to be custom built to cater to the requirements of the application that uses it. So analytics tools can help you to effectively handle the data. So there can be time series analytics, there can be spatial analytics, structures can be uncovered through these analytics. Predictions can be made. Not only predictions, you can go one step ahead and you can make prescriptions, right? So prescriptive analytics is very important. Streaming analytics for multimedia data. So these are all like different types of analytics that are characteristic of IoT implementations, which will have to be implemented depending on the specific IoT deployment or the requirements in hand. So it starts all the way from generation of the data to the analysis of the data. In between, you have acquisition of the data, the storage of the data. So for each of these, you need different tools. For the generation, so we have these IoT devices. For acquisition, basically, so you have different tools that can be used for the collection of the data, for the transportation of the data, for the pre-processing of the data. For storage, there are different tools like Hadoop, MapReduce, which I think are quite well known in the community by now. NoSQL databases, etc. And for analysis, there are so many different computational analysis techniques that are there. For example, Bloom filters, parallel computing, hashing, indexing, and so on and so forth. So like this, actually, I mean, these are only a few that I mentioned, but the complexity is enormous. So in terms of generation of the data, there is enterprise data, so let us say about online trading, analysis, online analysis, trading, etc., production, inventory, sales, financial data, etc., biomedical data, basically, so these are generated from, different sources such as gene sequencing, from medical clinics, medical R&Ds, etc. And there are different others, for example, computational biology, astronomy. Astronomy, basically, astronomical applications generate a lot of data, right? So, then the same goes for nuclear research as well. So in terms of acquisition, we are talking about data collection, data transmission, data processing, pre-processing. Pre-processing means, like, sometimes you have noise, redundancy, inconsistency, etc., which will, so you need to pre-process the data before you can actually process it, right? So you need to have a stage of pre-processing which can help you to clean, to curate the data that you receive raw, right? So the raw data will have to be pre-processed. So like that, actually, so after doing all of these, you get the data in a certain format so that you can use it. So the next little while I'm going to spend, as I promised, to give you a glimpse of some of the specific research works that we have been doing in the SWAN lab. And as you will realize that, so these concern analytics on top of the IoT data, but these are basically, so these are holistic solutions where data is one part of it, but so there are different other components that are also taken into account. So so as I said, again, I'm going to repeat that we do not have too much of time, and I'm going to cover some 6-7 works that we have done. Many others are available, actually. I just picked up these 6-7 works to give you a glimpse of what is out there. And in case you are interested, get in touch with me or follow the reference that is at the bottom of the slide, so that you can get further detailed information about the work that I talk about. So I will take one slide each for each of these works. So DLSense is one of the works that got published very recently in the IEEE Sensors Journal. And this is the work where we have created an architecture where distributed learning can be executed on data that come from virtual sensors for applications such as precision agriculture, right? So, so what we have done is we have virtualized the sensors, right? So the intelligent virtualization schemes have been executed in order to virtualize the sensors. So you get these virtual sensor nodes where actually these executions of different algorithms can be made. So DLSense basically talks about the execution of deep learning algorithms on the data. So the specific use case that we took is precision agriculture. However, DLSense can be applied for other application domains as well. So just as a case study, we took agriculture. So it starts from the user requesting a service to the service provider. Then the service provider basically provides the service by executing certain trained models which get trained offline. So you train the model and then you send the trained model, and on the trained model the data that comes through get executed, and this basically helps helps the user to get insights into the data that come from these physical sensors. So that's one of these. The second thing was about federated learning. So we applied federated learning on fog implementation, so fog assisted federated learning. So this particular thing was published in IEEE IoT journal again very recently. And here actually we are talking about distributed learning for delay sensitive applications in resource constrained IoT environments. So as you can see, this is the whole architecture. So at the very bottom layer you have the end devices, then comes the edge nodes, then the fog nodes, and then the cloud. So these are the 4 different layers of the FogFL architecture. And so the whole idea is to execute federated learning on distributed IoT implementations. So this is what we show over here. Mind you that these are not like full-scale implementations in real life. However, it has a lot of analytical component of the results, right? So a lot of these are that way, and in some cases actually we also have very small implementations that we have in the field, right? So field-based experimentation. This is actually a very primitive work. I just picked it up to show you, so what is important. So this particular work was published in the TNSM journal, IEEE TNSM, in the year 2016. Actually, it was done even a few years back. So here actually we are talking about sensor nodes or IoT nodes which misbehave, right? So which misbehave. So there are so many different types of misbehaviors that are there. Those have been there in the literature, but we identified a new type of misbehavior, the transfaulty misbehavior, where the nodes, they can sense, however, they cannot basically communicate, right? So they cannot communicate. So here also in transfaulty there are two types. One we call as the dumb nodes, which I'm not going to talk about now, so which was published even before. And then the transfaulty nodes are a specific type of dumb nodes where so these nodes get affected due to radiations, radiation prone areas, for example in nuclear, close to nuclear power plants and so on. So this is basically so how you can handle data when these nodes themselves misbehave, right? So how do you handle the the data from these nodes when these nodes themselves they misbehave? So this is what we did in our work that was published here. Another work which got recently published in IEEE Transactions on Parallel and Distributed Systems is how do you handle data from IoT devices which are redundant in nature, and sometimes, because you see, if you are talking about IoT deployments, so IoT devices themselves have very limited memories, right? So for maintaining congestion-free operations, mostly what happens is the data that is collected from these networks, many of these data are discarded instead of being transmitted remotely for further processing. Particularly, if there is repetition, etc., etc. So you discard a chunk of the data in order to save certain network bandwidth, right? So we proposed this timed loop storage concept, this TLS concept, time loop storage, where the data is distributed, and so the underutilized bandwidth of the local network links are utilized to distribute this data for sequentially queuing them on computational platforms, and taking them and operating them whenever the resources become available at the intended IoT nodes. So this is basically the time loop concept, and here actually the sequence packets are executed one by one or sequentially on the target IoT device, and the remaining packets which are currently not being operated on, they distribute and keep looping over the network links until they are required for processing. This is what I just told you, right? So this is what we do, that we distribute the data that is not urgent, that is not required to be as such sent, and then we distribute and we call them whenever the resources become free. Otherwise, they stay in the network, looping in the network, in the neighborhood for certain duration of time. So the data is important. So the data comes through, and the data, IoT data has the big data characteristics, and so on. So I see that I am almost close to the time that has been allotted to me. So I just wanted to touch upon over here that whenever you are talking about
Professor Sudip Misra,
yes.
we actually have a few questions and we are almost out of time. We'll be able to
summarize
them
in 2 minutes maximum. Okay, is that okay?
Sure, sir.
Okay, I'll just take 2 minutes. Okay, so this big data will have to be handled at the data centers, and for this you need to structure, you need to architect these data centers appropriately. So we did some work over here as well. So then how do you integrate multi-UAV networks, because this is very important, and how do you do clustering of the data that comes from these IoT deployments? So the last thing that I wanted to talk about is blockchains, right? So because securing the data and the devices and the infrastructure is very important. So how do you apply blockchain concept to secure the infrastructure, the data? So this is very important, and safety as a service is one of the concepts that we proposed, where, as I was telling you earlier, like the industrial data, safety is very important, right? So so you need to take care of it. So we came up with a safety as a service architecture for industrial applications. And in case you are interested, please have a look at the reference that is given at the bottom of the slide. So we among the works that were available for blockchain at the edge, we did one of the first. This was one of the first implementations of blockchain at the edge, which was published in the IEEE transactions on parallel distributed systems. So the data will have to be handled, as I said. But how do you handle, where do you store the data? For this, actually, there are so many different databases that are available that are actually used for IoT implementation. And in our group, actually, in the actual projects that we, where we are deploying in real life the data. So these databases like InfluxDB, CrateDB, MongoDB, these are some of these popular databases that are used along with, in the context of IoT deployments, right? So I'm not going to go through them, but what I wanted to highlight is these are very important aspects that will have to be considered. So which database you are going to use, not like, any database will work for any implementation. So which database you are going to use, how do you secure the data? So these are all like different, considerations that will have to be taken into account. Thank you so much. And I'm just on time. Thank you.
Yeah, thank you, Professor Sudip Misra. Let me quickly introduce to you Mr. Ankit Mathur, who is the Chief Architect in NAS and Unstructured Data Storage at Kharagpur Technologies. Hello, Ankit. Very nice to have you here. Please, you can.
Hi, Anvit. Hello, Professor. A very good morning to all of you. Dajia Hao, Ola. Yeah. So it was a very interesting talk, Professor Misra. And especially when you mentioned that IoT devices, it could be pretty much the chair I'm sitting on. And over a period of time, the weight I have gained, and it might have the capability to analyze and boot me out, saying like, you can't sit until you go and take a walk. So scary thought. Moving on to some of the questions. There are some questions from the audience. Some are more of a comment like, will the DL sensor and virtualized sensor concept increase the cost of the deployment itself? What's your take, Professor?
Yeah. So no, not. I think, so it's a completely different business model altogether, right? So I do not know, those of you who follow my works, many of you might be aware of, sensor virtualization is something that I have been working on since long time. We came up with the concept of something called sensors as a service, right? So sensors as a service. This particular concept, actually, those of you who do not know, and in case you are curious more about it, you can, just do a sensors as a service with my name, and you will be able to see the earlier works that were published, the initial works that were published on sensors as a service. So actually, there we are talking about sensor virtualization. So sensor virtualization is important, and it is about cost reduction, right? So it is about cost reduction and how you can cut down on the cost, right? So this sensor virtualization, sensors as a service, basically, so it's a completely different business model where you are talking about, sensor cloud service provider. It's not sensor service provider, right? So we are talking about a virtualized sensor service provider, right? So it's very similar to what you have for the traditional cloud computing, where you have a cloud service provider. So here actually it is very similar, and you are talking about a sensor cloud service provider. But the thing is that what I wanted to highlight in the context of the question that has been asked is that virtualization of, virtualizing the sensor nodes, right? So sensor virtualization means virtualizing the sensor node, right? So that's what is important. So conceptually it is good. Let me tell you, conceptually,
if you can throw in an example or two of like
so conceptually
virtualized sensors.
So conceptually it is good, because so what you are doing is that so let us say that so you there are certain types of sensor nodes, sensor data, which is important to multiple stakeholders, right? So for example, the temperature of a particular city, right? The temperature at different locations, geolocations of a particular city, the barometric pressure, etc., or you can think of something else also. So now this data is important for multiple stakeholders, starting from the government officials all the way up to, let us say if you are talking about, like, let us say farming, for example, right? So farmers, or you can think of somebody else, meteorologists or whoever, right? So it's important to multiple stakeholders. So conventionally, what used to happen is that everybody will have, whoever needs the sensor data, they will all have to individually, they will have to go and deploy the infrastructure, right? So that basically increases the infrastructure cost, right? So here actually we are talking about that there will be a sensor cloud service provider who is going to deploy these sensors, and there will be virtualized instances of these sensors through which the data can be retrieved by multiple stakeholders depending on the requirements that they have and the money that they will be paying. So the in essence, basically, you are not, if I need access to the sensor data, I'm not going to go and deploy another sensor network. I am going to rather take advantage of the sensor deployment that is already there in place, and I'm going to use it. And I'm just going to, it's a pay-per-use kind of model, so I'm going to pay for whatever I'm using.
Sure. So yeah, there are a couple of other questions as well, but since we are short on time, we'll try to get those questions across to you and get the answers and get it back to the audience. It was a very interesting talk, and I think with the IoT, we have a good segue into our next talk as well. So back to you, Anvit, and a great thank you to Professor Misra.
Thank you, Professor, and thank you, Ankit. So you can also answer the questions in the Q&A box if you have the time. I will greatly appreciate it. Over to you, Fatima.
Thank you so much, ladies and gentlemen. I'm sure we all agree that this was a very, very informative session. Thank you so much, Professor, for that. We have many, many more sessions coming up. Well, ladies and gentlemen, all of you have just tuned in. This is just the beginning. We are done with 3 segments and sessions from the time we've begun. Now we're going to quickly dive into our next session.